Begin recording. So our speaker today is Yuchen Zhu. She's a PhD student at the University College London, working on causal inference and causal machine learning, advised by Matt Kushner and Ricardo Silva, also working extensively with Arthur Gretton on kernel methods and their application to causal inference. Today, she's actually going to be talking about some work that was done while visiting Amazon Research Tübingen. And overall, today we're not going to have kind of our proper discussant slide, but we are shifting gears from the focus that has been on causal representation learning, where we've really assumed a kind of generative model where we assume that it's some ground truth latent variables that are generating the observations we see. And now we're going into kind of causal abstraction, where we kind of take the reverse view and we go from some system of causal variables at the micro level and try to abstract those to a macro level causal system. And this kind of will take us into a few talks on this set of works. And this is, I think, going to be a great place for us to start. So thanks, everybody. Welcome, everybody. Thank you, Yuchen, for doing this. And feel free to post your questions in the chat. And Yuchen, if you want to save 5 or 10 minutes towards the end for discussion, I think that would be great. So take it away.
Sounds great. Thank you, Chandler, for the introduction and for introducing me and for inviting me. Sorry. I'm very happy to be here today to talk about causal abstraction. So this work has started and mostly completed when I was interning at Amazon Research in Tübingen, working with Dominic Jansen. And it was also with Kailash Budatoki and Jonas Kubler. It has actually since become a topic I'm deeply interested in. So I'm very happy to have the chance to share this with you here and hear your opinions and perspective. And during the talk, please feel free to interrupt me whenever and ask questions. So the topic of causal abstraction is motivated by noticing that while we often find stable relationships among microvariables, for example, thermodynamic laws are very robust physical laws which describe the kinetic energy of particles, we often are only interested in cause effects among macro variables. For example, how does changing temperature impact plant growth? Note, it is not immediately compatible with the existing language of causal inference to describe the relation between temperature readings on a thermometer and plant growth, because readings on a thermometer is typically thought of as an effect of the particle movements, right? And intervening on the thermometer would remove the arrow from the particles, and then it would say that there is no impact of changing the temperature reading on plant growth. So the first conceptual realization that allows us to formulate causal abstraction is to realize that we're not interested in the thermometer reading, but rather we're interested in the concept of temperature. Importantly, temperature and particle kinetic energies follow a logical relationship rather than a causal one. So here I'm being kind of wavy about what I mean by a logical relationship, but essentially the point is changing the temperature must change the kinetic energies. So this is a symmetric relationship rather than an asymmetric one, which is typically how we understand causal relationships. So then because changing the temperature must change the kinetic energies, this would propagate the change to plant growth. And thus we're able to draw an arrow from temperature to plant. So the important point here is that changes on the macro variable must get implemented on the micro variables. So now, as long as the resultant temperature is the same, the growth of plants doesn't care about how exactly this temperature is implemented in terms of the kinetic energies. And in this situation, we're actually able to talk about a causal model for temperature and plant growth. However, in general, causal effects of macro variables are ambiguous. And here's my favorite example. We have a simple model with two independent causes, x1 and x2, and an effect variable y. Y here is just a simple linear model of x1 and x2, and the coefficients with coefficients alpha 1 and alpha 2. And Now I'm interested in the aggregated effect of x bar on y, where x bar is the sum of x1 and x2. Let's say I seek a linear model of x bar on y. So I ask what would be the value of y if I set x bar to be 1. So we must implement this on the micromodel, right? So if I implement this by setting x1 equals 1 and x2 equals 0, then I'm going to run the recursive causal model and get y equals alpha 1, which seems to suggest that I should conclude y equals alpha 1 times x bar. But I could equally implement this by setting x1 equals 0 and x2 equals 1. Then I run the causal model again, and that would result in y equals alpha 2, which seems to suggest a different model, which is y equals alpha 2 times x bar. So this is the first challenge of causal abstraction, which is that the effects are ambiguous. Now, Rubinstein and Weichfeld 17, and et al. 17, and Beckers and Halpern in 19, they disallow this situation by proposing exact transformation and stronger notions, requiring that different microscopic implementation of a macro intervention need to equally affect the aggregated downstream variables. So the first way of dealing with this problem is to not allow it. However, it should not be hard for you to agree that this is a strong requirement. And okay, so that's the first problem. And actually, the problem can get even worse, which is that moreover, if you're so if you think that the ambiguity of effect is somewhat obvious, because obviously different ways of implementing would lead to different outcomes in the effect variables. So if you think that's obvious, less obvious is that even the causal structure of a macro model is ambiguous, which we will show later. So the first challenge can be expressed as follows. I have a micro variable model, which is simply a causal model in the standard sense. I ask what are the correct causal links among my specified macro variables. This question can be impossible to answer because different realizations of the same macro cause variable setting give me different effects. So that was the first challenge. And now the same question can also be asked backwards. If I have already decided on some causal link and some structural function on my macro, like among my macro variables, how can I implement my macro interventions so that the effect dictated by the macro level model is realized? But decide I want this model. How do I implement my macro intervention so that I actually get this model? So one might adapt the existing idea of pre-specifying a distribution over micro interventions. So this is what Beckers et al. Did in 2019, where they first require, you can think of it as a prior distribution over interventions on your micro model. And then you can, and then via your aggregation map, you can kind of get this posterior distribution over your micro level interventions. So two issues arise from this formulation. Firstly, gaining a consensus on this prior distribution over micro interventions is tough because there are so many of them. And the fact that it's difficult to gain this consensus is kind of why we're trying to do causal abstraction. And the second issue is this yields, so even if you can like specify this prior distribution, this can yield a spread of micro interventions for which actually none of them might individually align with the intended macro model. So all of them are wrong, but on average, they seem to give you the right effect on the macro level. So this is also undesirable. And so far, the authors have not offered guidance on how to actualize, at least in the original paper, they have not offered guidance on how to actualize micro level implementations while always maintaining consistency with the macro model. So the third challenge of causal abstraction stems from the fact that the micro model might not even be fully known. Sometimes we may only know isolated facts about the causal model. For example, we might know that it's confounded, but we might not know the exact structural equations. In that case, it is even harder to reason about micro-level implementations, and sometimes it might not be possible. So questions from previous challenges are still relevant here. So how do you implement things? How do you ensure certain properties in the macro model that you want? But you have to answer them also without knowing fully the micro model. So since many talks before this one have been about causal representation learning, I wanted to say a few words just comparing them, but I think also Chandler at the start summed it up very nicely for me anyway. So just maybe for the people that joined afterwards, just very quickly, causal representation learning is about saying, I assume there is a latent high-level ground truth causal model, typically lower dimensional than the observational space. And the goal is to identify it from observational and interventional data from my downstairs. And meanwhile, causal abstraction posits that the low-level high-dimensional model is the one containing the robust causal relationships. And we're interested in doing this compression to get to the high level while retaining some notion of consistency. So here now I want to give you like an overview of the landscape of existing work. So early work starting from Rubinstein, Weichfeld et al. 2017, they propose exact and approximate transformations. And the one feature about that body of work is that usually they start by considering a set of interventions in the micro model, and then they push those forward to the macro level, and then they compare the models in the macro level. Meanwhile, more recent work have started to consider a more direct link between macro interventions and their micro level realizations, although they haven't started calling it by micro level realizations, and they have only considered specific types of micro realizations. And our work is the first to consider a family of macro models as a function of micro realizations. And we explicate consequences of this formulation. And we also talk about differences within this family of macro models, which you can think of as parameterized by micro realizations. Okay, so what are the use cases of causal abstraction? It turns out that most variables that we care about just are macro variables, right? So this is already a short answer, it's everywhere. But some concrete examples include in 2016, Kalupka et al. Used it to learn causal features of brain neuron activities, as well as the climate phenomena of El Nino. And perhaps excitingly for the machine learning community, Geiger et al. In 2021 also showed that you can use causal abstraction ideas to abstract neural networks, which you can think of as a massive causal graph. So, so this has implications in AI safety. And some colleagues at Amazon in just 2023, they have applied it to the case of cloud computing, where macro variables are the average latency of some service over all requests within some time interval. And when I started this project, it was also motivated by strategic planning of large businesses, where performance metrics are usually aggregated variables. Not sure if there's a question. No question, good. Okay, so now I'm going to introduce the concept of micro implementation, which is a key concept that we introduce in this work. So consider this micro causal model, which is nothing but a causal model in a standard sense. I want to aggregate together x1 and x2 and leave y be. As mentioned in the motivating example, the aggregation link is a logical link associated with the aggregation maps pi x and pi y, which are surjective maps from the state space of x and the state space of y to their corresponding macro variable state spaces. Here you can think of pi y as just the identity. And a macro intervention at x bar is simply a perfect intervention on the macro variable x bar. However, for us to reason about the effect of do x bar, we must associate it with a probability measure over x, denoted p do pi bar x. So whenever the aggregation map pi is clear, we can drop it. And the measure must be such that whenever x is in the support of the measure of this p do measure that you've specified, we must have that pi of x gives me x bar. So it's a fairly intuitive definition. So here do x bar then means I enforce the soft intervention of p do x bar on x1 and x2, which and in doing so, I'm removing the edges from n1 and n2.
So
And
is
this
is this what you were referring to when you said the family macro models is a function of the micro-realizations? Is that this pi do x bar is defined separately for each x bar?
Oh, a good question. So, no, that's not yet what I mean. What I mean is for the same x for the same value of x bar, for the same state for x bar, you can already define different measures, right?
Yeah.
And each different measure already give you a different effect. And then you can, of course, also think about like defining a family of measures over different x bars. Yeah, but when I say a family of macro models, I meant different measures defined on the same x bar. Yeah.
Okay.
Yeah, thanks. So so this definition allows us to depart from previous narratives and always ask for the implementation over micro models whenever we want to talk about a macro intervention. So it's not defined until you've told me what the realization is. So so now I'm able to compute the impact of my intervention by simply running the causal model up to y, which involves a marginalization at x, and then computing y bar using the surjective map from y. So now we're going to illustrate the first result in our paper, which is that confounding is ambiguous. So we will, yes.
This is a question from Crick in the chat, asking, is the logical relation the same as what the causal feature learning paper refers to as a constitutive relation? Or I guess what's the relationship between these things?
Yeah, I think that's right. These are basically the same thing. You want to separate them from causal relations. Yes. Okay, thanks for the clarification questions. So yes, so confounding is ambiguous. So we illustrate this again using a simple example. There are two shops, each with two products. My micro model is exactly the same as before. X is the number of first products sold. X2 is the number of second products sold. Y is the total revenue. Alpha 1 and alpha 2 are the prices of product 1 and 2 respectively. And the micro model, same as before. And Y is just the linear combination of X1 and X2 with coefficients alpha 1 and alpha 2. X1 and X2 are given by those mean 0 and variance sigma squared 1 and 2 Gaussians. The aggregation map for X is the sum, and for Y is the identity. So so you can think of X bar basically as a total sales, and Y is the total revenue. So now both shop owners, they ask themselves the question, how does changing total sales change total revenue? Note that this is actually a question that can be asked on a much larger scale. Imaginably, Amazon can ask this question over their millions of products when they don't want to reason about each product individually. So now the pink shop owner conducts an experiment. They randomize the number of units sold with basically just the conditional distribution, Px1, x2 given x bar. Sorry, there should be a bar here. Implementing the intervention like this allows us to compute the interventional distribution of y bar, which ends up as just the conditional distribution of y bar given x bar, right? Because you've done nothing but marginalizing. So if the shop owner uses the interventional data to work out the potential outcome, y bar at x bar, they would just find the standard regression equation, where observationally the residual is independent of x bar. So the pink shop owner would observe that the observational conditional distribution of y bar given x bar is the same as the interventional one. So they conclude that the system is unconfounded. Now the blue shop owner also conducts an experiment. They alternate displaying item 1 and item 2. On day 1, they display the first item, observe how much it got sold, and then they turn up or down advertising to make sure that on day 2, they sell the amount of product 2 to make the sum x bar before they just close the shop to stop selling more. And then they repeat this. On day 3, they display the first item again, and so on. This results in the implementation as shown. So here, x bar and x2 are randomized as follows. So x1 is just free. X bar is just taking its original marginal distribution. But x2 is always sold to make the total x bar. Okay, so now they're also going to take their interventional data and try to work out their causal model. They will work out this causal model, which is that y bar equals alpha 2 times x bar plus n tilde, where n tilde is alpha 1 minus alpha 2 times x1. So maybe to see this more like directly, why it ends up being a model like this. So if you think about in interventional land, the potential outcome of y bar given x bar, that is just alpha 1 times the number of first items sold. So that's alpha 1 times x1 plus alpha 2 times x bar minus x1. And that's your second item sold. So you rearrange that a bit and you end up with this structural equation. Okay, but note that now in the observational distribution, n tilde is correlated with x bar. So the blue shop owner, comparing the conditional distribution of y bar given x bar before and after intervention, would conclude that the system is confounded. So this leads us to conclude that that confounding is ambiguous. But actually, let's pause and scrutinize this a bit more.
Okay. Can I ask before we go on? Just to clarify, so is the problem not that it's just that the blue shop is conditioning on the aggregated variable, or is it like, you know, the policy they're implementing conditions on this aggregated variable, that, you know, this x bar variable, or am I misunderstanding that? Okay.
Yes, the blue shop is conditioning on the aggregated variable when they implement the policy. That's true. But so is the pink shop. So but you are right. The problem is exactly that they've, like, the conditional distribution that they've used is different.
I see.
Yeah.
Okay.
And this is exactly the problem. And it's also exactly why we need to scrutinize this more. Like, isn't this just the problem of using different policies? Why should we even call this confounding? Yeah.
Yeah, I guess the thing the thing that's sort of subtle about this is that the macro state is kind of influencing the policy of the micro state in a way, or in a way that doesn't feel like just a logical relation anymore. Maybe I'm misunderstanding this, but like, you know, like temperature, the sort of classical like temperature, pressure, temperature, average velocity is just like this logical definition. Nothing about the temperature influences how the particles move around in a system.
Well,
Where
I think it's because you are setting you have a target intervention at the macro level that you want
I see.
to be the thing that's being done, and then you have different ways of implementing it. So it's like, do I change the average temperature in a room by like having like, you know, heaters all around, or do I like take like one little like, you know, ball of gas in the corner and make that really hot? Like those are two different ways of changing the average temperature.
I see. So we're defining our targets at the level of the macro variable, but and then allowing the micro variables. I guess there's a sort of strategic aspect in this that sort of feels like subtly different, but maybe I'm just overthinking it. You know, the policies are being set at the level of the micro variables.
Yes.
You know, the individual shops are choosing their behavior in order to achieve a sort of macro level goal, and that feels subtly different to just like the sort of simple aggregation function. But maybe they're the same. I don't know.
So okay, so here's the thing. The aggregation function is a function going from the micro variables to the macro variables, right?
Yes.
But the policy function essentially goes from the macro variable back. So here, maybe I didn't get the question right, but I think here one thing that could cause confusion is the aggregation map tells you nothing about the policy, because the aggregation map at most give you a pre-image, right? The aggregation map is going from the micro states to the macro states. And then now you say like, okay, I want the macro state to be this particular value. The aggregation map can't tell you how you're going to implement it, apart from like it can only tell you the set of micro states that's compatible with your macro variable. So what you need to specify in addition with the micro realization is how exactly you're going to choose among those compatible micro states.
Good. Okay. Yeah. I maybe this is sort of a distraction, but the thing that feels subtly different about this setting to say the physical system setting is the way the micro variables can interact via the macro variable.
Okay. Yeah, now I understand the question. That's a good question. Thanks. So in the in your physical setting, for example, like heating up the room.
Yep.
There are like stronger relations among your micro variables just because of physical laws.
Yes.
Like you heat up the room with like just a heater at just one point of the room compared with heat up the room with like heaters all over the room. Like at first it's going to be different how the particles move, but you run them for a while and the equilibrium distribution should be the same of
yes.
Yeah. So and this is because like physical laws are very strong.
Yep.
But here we're considering cases where you kind of get to make the physical laws. Like,
and kind of importantly, like here, you know, like I don't know, say I have to meet a sales objective. Like if I know Crick is going to do all the work, I could choose not to do things. So like my behavior can change as a function of what I think other shops will do in a way that's not true of the physical laws. Like speeding up one particle doesn't change. You know, if we're two particles in a room, I can sort of speed up one particle and not have it influence, or maybe does have it influence, but it doesn't change like there's no sort of beliefs or strategy involved. Whereas I think this becomes game theoretical. Anyway, I feel like I'm derailing you. So let me let me leave that at that. We could do this in the discussion.
Yeah, I think the important point, which did come out of this very good question, is that there is in general more degrees of freedom in this setting that we're considering than physical systems where the physical laws are strong. Yeah. There's a.
Yeah.
Yes. Okay.
So Hib's suggestion seems like a good example if you want to elaborate on it. But yeah, I agree. We've also spent enough time here. So
yeah, so I would like to go on just because I want to justify why we should call this confounding. Yeah, so why should we call this confounding? As Jason correctly pointed out, we're just choosing different policies. So one way of thinking about this is through the observer's point of view. So from the observer's point of view, the shop owner is simply considering X bar, Y bar, and N tilde, which is the residual from, so N tilde is the residual from the interventional data. They then observe that observationally N tilde and X bar are correlated. Then we can use Reichenbach's principle to conclude one of the following. Either N tilde causes X bar, or X bar causes N tilde, or there is a common cause connecting N tilde and X bar. Now, the second option is ruled out because the micro-realization does not change N tilde just by definition. So we're left with option 1 and 3, and they would suggest that both of them would suggest that there is confounding. So this is kind of a philosophical justification using the observer's perspective, by which I mean like the observer can only see, in a way, X bar, Y bar, and N tilde. So we use that perspective together with Reichenbach's principle to conclude that it makes sense to call this confounding. And I also want to talk about another perspective from change of coordinates, which I believe really shed light on a deeper level. So in this 2D plane, I draw the contour lines, which are the ellipses of the density function over X. I also draw the contour lines of Y, which are the dotted lines. Now I can add the contour lines of X bar, which are the blue lines. And then the intervention that changes X bar to a different value of X bar can be represented by a vector on the 2D plane. And note that there is ambiguity in this vector if we want to move from one value of X bar to a different value of X bar, just because like all 3 vectors here, they land in the same contour line of X bar, right? But anyway, let's go back to the original one. Now note, there is a linear function of x1 and x2 that would have its contour lines in parallel with this vector. And we call the result of this linear function n. Implementing the intervention according to the blue vector would keep n invariant, which is exactly what we were doing. In this view, aggregation is just doing nothing more than changing coordinates of the causes from the x1, x2 system to the x bar n system. So thinking of x bar and n as causes of y are just as valid as thinking of x1 and x2. Now, of course, simple probability theory tells us that the functions of 2 independent variables are no longer generically independent. So x bar and n are in general dependent causes. And then we can apply Reichenbach's principle again and conclude that they're confounded. And also cases where we do yield an unconfounded aggregated model also admits a geometric interpretation, which is that it would be when, like it happens when we can find transformations of the cause variable state space that yield independent variables. So now this leads naturally to the next question. What micro-realization keeps unconfounded microvariable unconfounded? This feels similar to how partial derivatives are ambiguous because they're, okay, yeah, that's a cool connection. Right, so what micro-realization keeps unconfounded micro model unconfounded? Well, so this is a simple and positive result of the paper. We can always use the conditional distribution, right? So in the case with two high-dimensional micro variables, we can always construct the unconfounded macro model by choosing the conditional distribution as micro-realization. And we call this the natural micro-realization. And we call the macro intervention associated with it the natural macro intervention. And so the importance of this construction is that it provides an option for aggregating cause-effect relations while also keeping the graph consistent. So we don't have to we don't have to add this backdoor arrow after we do aggregation. So recall challenge 3, which is that the exact micro level model is not known. One desirable property of the natural micro realization is that we can define it without knowing the micro level structural equations. As long as we know that the underlying micro level structural equation, the underlying micro model is unconfounded, we know that the natural realization would keep this no confounding property. Okay. So I think I'll just, in the interest of time, I'll go through this rather quickly. So I just wanted to show an example of applying this to a nonlinear and non-Gaussian example. So we have some additive noise model here, and my desired macro variables are, so I want to aggregate together the exogenous noises. I want to aggregate together my x's, and I want to aggregate together my y's. So now I look at this the sum. So the first term of my y bar, which is the sum of the fj's. I realized that so I call this w. I realized that w can equally be parameterized by x bar and this other variable that I construct, just as well as it can be parameterized by my xj's. And here, what are phi and psi? They're essentially functions such that phi fixed at x bar is the inverse of psi fixed at x bar. And I substitute this back in, and I yield this sort of new structural equation of y bar, under this change of coordinate systems, with my phi, and m being the result of psi. So now, if I want to apply the natural realization, what I can do is I can choose my phi to be the inverse CDF of w given x bar. And that would yield my m to be just the uniform random variable. So what this is doing is essentially at x, at x bar, I just ask what is the conditional distribution of w given x bar. And then I use this m variable to pick a state via this CDF construction. Yeah. Okay. So this comes out of natural realization, which works and gives an unconfounded model, because here m is always going to be uniform regardless of what n bar is. But it's not the most interpretable one. A more interpretable option would be we could think of the following, where let's just think of a linear model again, where fj(xj) is alpha j times xj. And you could think of this as the revenue you've made from selling xj copies of the products with price alpha j. And one way of constructing the noise variable is by requiring it to be the average price, which is here the total revenue divided by the total items sold. And here, for simplicity, I've required the V's to be 0. So this would yield the macro model y bar equals x bar, which is the total items sold, multiplied by the average price. And we can think of this model as representing interventions in which the business would sell products to an additional country with buying patterns comparable to their existing customers. So here we actually yielded a confounded macro model, but the noises are more interpretable. So just an example. Okay, so just now we've seen that natural interventions can keep an unconfounded micro model unconfounded. Can we ask the opposite question? If you start with a confounded micro model, can you kill the confounding by choosing an appropriate realization? And the answer is sometimes. Just let me organize the time a bit. So I think I'm just going to go through this example and then go into the outlook. So here I'm again considering the simple linear Gaussian example. And the only difference with my previous example is now my n is correlated with x. I'm asking whether I can find micro-realizations that'll make the interventional distribution of y bar given x bar the same as the observational. So I require my interventional distribution of like x given do x bar to also be a Gaussian distribution, and I can characterize it by its mean and variance. I compute both the observational distribution of y bar given x bar, which is just this, and I can also compute the interventional one by like taking this marginalization over x and n. After computing it, I get the mean and variance as follows. I'm only trying to match a linear linear Gaussian distributions, so I only have to match their mean and variance. Matching the mean would give me one condition it would give me the condition on my interventional mean. And note that I have full freedom in choosing my interventional mean. So this is fine. So this red condition can be satisfied. I just have to choose my expectation of x given do x bar such that it satisfies this equality. I also have to match my variance. In order to choose my sigma do x bar x to be such that it satisfies this equality is actually a bit harder than the red condition because the left-hand side is always at least 0. So one thing we need to require on our micro level model is that the conditional variance minus the variance of the noise is at least 0. And as long as this condition is satisfied, I note that the blue equality can be satisfied because I can choose the sigma do to make the left-hand side arbitrarily large because alpha is not proportional to 1. If alpha is proportional to 1, this does not work because alpha is proportional to 1 would just give me already like alpha transpose x would just already be x bar. the sigma do x bar have to have 1 as an eigenvector with eigenvalue 0 because I'm conditioning on x bar. Because I need to do this intervention so that all of my x's in the support need to add up to x bar. But as long as alpha is not proportional to 1, I can choose the other eigenvalues in this sigma do x bar such that the left-hand side is as large as I want, so I can make this equality. But now, the question is, when do I have micro models that'll yield unconfounded macro models, right? So when do I have a fine-grained micro level model that will satisfy this equality? So note that the variance of y bar given x bar is just the variance of alpha transpose x plus n given x bar. And in the case where alpha is proportional to 1, we can ignore the first term because the first term is just x bar and then we're given x bar. So this, in terms of variance, it doesn't add anything to the variance. And this would not be possible because then the variance of just n given x bar is definitely smaller than the variance of n because by assumption, n is correlated with x bar. And we're in a linear Gaussian model. However, if as long as alpha is not proportional to 1, we can make the variance of the first term inside this variance arbitrarily large as long as we scale up alpha indefinitely in the same direction. So when we scale up alpha, the variance is just going to get bigger and bigger, and at some point it's going to be greater than the variance of n, and then it'll stay bigger beyond that. So we have convinced ourselves that at least for a good portion of the model space, we have this confounded micro model for which we can construct unconfounded macro models. So this is the linear Gaussian example, which we conclude that sometimes is possible. In the paper, we also have this technical result concerning general categorical variables, where we also show that essentially sometimes you can construct models such that, so here are the x are the micro variables. I'm just going to say the results. So we show that you can construct models where x, y are confounded, x, y bar are also confounded, but x bar and y bar seems unconfounded. And you get this result because because when the state spaces of x, y, and z are much, much larger than the state spaces of x bar and y bar, sometimes you can kind of make the confounding cancel out with itself if you choose the appropriate micro-realization. So here, I do want to be transparent about one thing, which is that in the linear Gaussian case, we have only considered matching the distributions in the observational and interventional land. So this, we can consider this as only a weak form of no confounding, because really what you would expect no confounding to say is the interventional residual is the same random variable as the observational residual, right? So requiring equality on the random variable level is stronger than requiring equality on only the distributional level. And actually for the linear Gaussian example, once we start to require equality on the random variable level, it's no longer true. But so this is where our work got to, and analyzing this stronger sense of no confounding need to be left to future work. In the paper, we also provided some, let's say, early results for generalization to n variables for this natural intervention. I only have time to talk about it quickly here, which is that basically when can you when you have 3 high-dimensional micro-variables and you have a chain, when can you draw this downstairs model? And you don't have any problems understanding the story for how do you randomize X. You can just use the original definition of natural intervention on X. So you randomize it using the conditional distribution of X given X bar. But when it comes to randomizing for Y, you have a choice. Do you randomize using Y given Y bar, or do you randomize using Y given Y bar and X bar? Now the problem is because in the aggregated land, in general, Y bar does not block off the information from X bar to Z bar, right? So knowing like there is no Markov property that says Z bar is independent of X bar given Y bar. So knowing X would kind of change your natural intervention. So this yields this kind of lead to this condition that if you want to draw the downstairs model, you need to require that in the observational, in the macro variable land, you also have that X bar is independent of Z bar given Y bar. And once you have that, randomizing Y according to Y bar, according to Y given Y bar and X bar is the same as Y given Y bar, which mathematically is quite obvious. But it has this implication for aggregation here. And another piece of early results is, so basically what we're trying to do is to generalize this idea of natural interventions to draw consistent graphs for bigger graphs. So in the case where you have so 3 micro level variables that form this confounding structure, when can you draw the corresponding graph in the macro variable land without drawing also some arcs, right? So this is really a very preliminary result, just want to be honest. The result essentially says that, so the problem is still in how do you randomize this Y, basically, because how do you randomize X is clear, because X is the source variable, so you still randomize it using the original definition of natural intervention, and Z bar is the sink variable. So it also, so how do you randomize it has no implication. So how do you randomize this Y? It turns out that we can satisfy, so one sufficient condition of satisfying the backdoor criterion, here we have written down a macro variable analog, which is the potential outcome of Z bar given Y is independent of Y given X bar. So in order to satisfy this backdoor criterion, we have to randomize the micro-realization of Y conditioned on both Y bar and X bar. So although this is a sufficient condition, it is certainly problematic because you're saying to implement an intervention on Y bar, I need to look at its confounder, which is different from the natural way of talking about perfect interventions. Yeah, but this is a preliminary result. So okay, so I'm going to skip this slide because this is just a more general version of backdoor adjustment. And so in summary, we former definitions of consistency basically ask for all of the different microscopic implementations to result in the same effect. So this is restrictive because it's very hard to ask for people to directly come up with macro models that has this property. And former definitions also don't provide guidance on how to find abstractions that satisfy them. Meanwhile, almost all causal models we're interested in are on macro variables, but we have shown that ambiguities can arise both in terms of effects but also even causal structure. And by analyzing the relation between micro and macro models, as well as micro-realizations, the theory that we provide in this work gives an understanding of what cause and effect relations mean in terms of implementation of interventions. And the outlook after this, and this is not vacuous because we're already working on it, is the theoretical analysis of the n variable case. So how do you generalize to n variables? And what I personally believe is really close to the heart of the future of this direction is this change of coordinate view of causal abstraction. And that needs to be more fleshed out. Yeah, thanks for your attention. So this is joint work with these lovely colleagues at Amazon, especially Dominic.